Good morning, this is Deep Generative Model. This week we continue to talk about the language models. We're going to talk about different ways to do tokenizations and different methods to train and pre-train your language models. Next week we are going to the details of the implementation. The major resource we are going to use is GPT. You can see a link right here. The author of GPT is Kapasi. He has a lot of different reports regarding the implementation of GPT, including the currently very trending and famous one is LLM. So you can search the LLM.c. It is using only C and CUDA to implement the whole GPT architecture. The one that we are using is GPT, which is a bit older, but it uses PyTorch and is more suitable for educational purpose. There's an updated version which is called Nano GPT, which is also a very good source for learning how GPT works. But I think it is more suitable to start with GPT. So let's go to today's topics. Several weeks ago, we have talked about the character level language model and also n-gram, but the character level model is not the only way to modeling the language. Other popular ways are word level or sub-word level language models. So currently, the most popular one is sub-word level, or we simply call it token level. Because although they start from the sub-word level tokens, they are just a way to build a dictionary of tokens. And these tokens may be a character, a word, a sub-word, or maybe even some inter-words. So why not just stick with character level modeling? The thing is, we are not fully solve the language problems, so we don't know which one is the best. Since there are many different approaches, there's no reason we should stick with just simple one. So people try different approaches. Each approach has their benefits, strengths, and weakness. So for a character level language modeling, it is simple and straightforward. It is simple and straightforward. However, the model has to learn the language from very beginning. The model has to learn how to spell a word. Like an apple is A-P-P-L-E, because it doesn't have any prior knowledge of that A-P-P-L-E is a valid word in the language. So the model has to learn from spelling the word. And because language understanding is a very difficult task, so if we relieve the burden of learning spelling from the model itself, maybe the model can focus on more important part of the language like the grammar, the meaning, the semantics, or maybe the logic, the knowledge contained in the text data. So let's just explore what these other methods is. If you are starting from study English language, the word level tokenization is probably the most obvious or apparent way to start with, which means we use space and punctures to separate words. So for example, I like to eat apples and bananas. We can easily identify there are several different words like I, like, to, eat, apples, and bananas. And because all of these are common words that we can find in dictionary. So suppose we already have a dictionary, we can encode in each word by its corresponding number. There might be some small considerations that because this is apples, there's an S after the apple. So we count these two words as the same one. Should we count the apple the word? Should we count the word apple and the word apples as the same numbering? or we should use a different word, or we should use a different one. But I think that is just a small considerations. But either way seems to be reasonable approach, and we don't need to worry this too much because we have bigger issues. Because our dictionary can contain only finite number of words, there's a limitation. So a common method is to sort the words by their frequency. If a word is very rare to appear in our training data, we probably will discard it because it is difficult to design a model with a very, very large dictionary size. And after all, since this word may just appear only once or twice in the dataset, our model is unable to learn too much about this word from a dataset. So it is very common to have a size limit of a dictionary, and any word outside of a dictionary is labeled or mapped to UNK, which stands for unknown. But once you encounter these real words, it will be mapped to unknown. And all the model know is this word is an unknown word. The model knows nothing about this word. Another issue is people tend to be very creative when they spelling a word, and other people can understand this creative spelling. For example, I like to text my friends. Although technically this word does not spell correctly, people use this kind of spell. People use this kind of spelling, and even though you haven't encountered this spelling before, chances are you won't have any difficulty of reading this alternative spelling. Also, new words are invented time by time. For example, he's a fan of crypto mining. This word may not even exist before 2008. If a model encounters a word that is not existed when it's training, it will map this one to the unknown. But suppose this is the first time you have seen this word. Even so, you probably won't understand what exactly it means. You might have some ideas about what this word might mean. And also there are a lot of different people, and also in the text, people frequently misspelling words. So like this one should be love and this one should be CREAM. Still, people can understand it, but the model cannot because they will be mapped to unknown. And those are not the only issues, because there are many different languages in a word, and the splitting word by space and the punctures is not as general, cannot consider as a general rule among languages. So for example, for Chinese writing, there are no space between words, and so a word segmentation algorithm or tools is needed if we wish to apply the word level language modeling on Chinese. Also, there are many languages has some sort of a compound word or sentence word. So for example, this one is also a valid compound word in German. So the concept of word, or at least a finite dictionary of words, is not universal among languages. In fact, even if only English is concerned, there are still too many exceptions, like we discussed in last slides. Back in 2014 or so, word level language model is still a very popular approach. Like the word-to-vector model we introduced before is specifically working on words. And when dealing with the Chinese language processing, people are using Jeba or CKeep to do the segmentation, to do the word segmentation before feed it into a neural network. But right now we are expecting more. So the subword tokenization is the mainstream. So maybe like 5 or 10 years later, character level will come back again to be the mainstream. So let's explore some other method to do the tokenization. One of the famous method is BPE, the bypair encoding. So what is it? Bypair encoding is a tokenization method that reduces the complexity of text data efficiently, handling rare and domain-specific words. So it is an algorithm for building a dictionary of tokens that we can use. So the initial dictionary is simply all the characters or maybe all the bytes in your data. So that's our initial dictionary. Then we grow up the dictionary with more tokens. So at the beginning, each text and each byte or character is a separate token. So even with the very beginning, the dictionary can spell any words. So there will be no unknown at all. But we are going to enlarge our dictionary. The second step is to identify the most frequently occurring pairs of bytes in a text. So we observe the sequence, we observe the text, and if we find out some of the tokens, that is so after we find these frequent pairs, we add this pair into the dictionary. We can still spell every single word in a text with this new dictionary of tokens. But some of the spelling will be shorter because we have some new tokens. And then we repeat this process again and again to enlarge our dictionary until we reach some predetermined size of a dictionary. So here is an example taken from the transformer document of the Hugging Face. So first we start from the word level tokenization. So let's take for example this sentence. Do you love Transformers? We sure do. So not only this one has many English words, it also has an emoticon here. So if we are splitting these words by space, we can easily get don't you love and this smiling face and transformer. We sure do. There are certainly some variations, like we probably should consider also the punctures. Because if we don't consider punctures, we'll have something like a do dot, like a do period, or transformer question mark. This is probably not what we want. Here are some codes example of how tokenizers actually works. So this one is the tokenizer of the BERT model. So by given this sentence, I have a new GPU. It will split the sentence into these tokens. So you can see, although GPU is not in a dictionary, it can still spell it as GP and U. These two hashes means we should connect these two guys together. So here's another example that is the tokenizers of XLNet. As you can see that space is also considered as a character in this tokenizer. The particular tokenizer is using the sentence piece, which we are going to introduce a bit later. You can see that even though transformers is not in the dictionary, it can still split it into some more suitable segmentations like transform and earth. So let's go to the section of BPE and see how it works. So suppose we have a bunch of words that corrected in the text. So this means the word hug appears 10 times in our text. park appears 5 times in the text and so on. So at the very beginning, our dictionary only contains characters. So since these are the only characters that are used in this example, so this one is our dictionary. So we can spell every single words in the data, like this one, HUG, PUG, PUN, BUN, HUGS. Then we count the frequency. Then we count the frequency of each pair of. Then we count the frequency of the appearance of each pair of the tokens. So for example, here we have HU. So in this word, it appears 10 times. But HU is not only appears in this word, it also appears like here. It appears 5 times. So in our text, HU appears 50 times total. HU appears 50 times total. HU appears 50 times in. HU appears 15 times in total. HU appears 15 times in total. HU appears 15 times in total. And for example, UG appears in HUG 10 times and appears in park 5 times and also appears in hugs 5 times. So 10 plus 5 plus 5, it appears 20 times. It turns out it is the most frequent combination. The most frequent pair appears in our data. So we are going to add the combination UG into our dictionary as a new token. So we have a new token UG in our dictionary. Then we spell Then we spell every word by using our new dictionary. So we got here HUG here and the PUG and the HUG. Then we do this again. We identify the most common pair in our new dictionary. So after we get in the new dictionary, we do the process again. We first identify the most common pair in the spelling by using the new dictionary. We find out that UN is the most common one. So we add UN into our dictionary. Then we do the process again. And this time we find that HUG is the most frequent one. So although HUG has a longer length than other combinations like say PU or BU, but we are only focusing on the frequency. So since HUG has the most frequent, so since HUG is the most common pair, we are putting it into the dictionary. So we can continue doing so until we reach the predetermined limit of our predetermined size of our dictionary. Then we can stop and have our result encoding. So compared to the word level tokenization, it has two major differences. One is it uses an algorithm to construct the dictionary. The second difference is that just like the character level tokenization, if a word is not in the dictionary, we're going to spell it using the tokens that appears in our dictionary. So we don't have to use the unknown token at all. So as a conclusion, there are many benefits of using BPE against the word level encoding. One is the flexibility, because the encoding can be adapted into new testing text without that contains new words, and also because we don't use unknown. So if we are encountering some new words, the model will at least see a difference between different new words. They'll get a chance to guess what the word means. If we are encountering a new and unfamiliar language or text, we can simply run the algorithm again and generate our dictionary without relying on an existing dictionary. And when a new word is encountered, it will try to make the new word as a combination of the existing tokens. Another similar algorithm is word piece. This is another popular tokenization method, and it works very similar to BPE. It is used in models like BERT and Google's T5. The key difference is the way that word piece choosing the most frequent simple pair. In BPE, we simply count the number of the pair used in our text. But in WordPiece, it considers the relative frequency against the tokens in the pair. So for example, if we're considering the combination UG, so let's consider an extreme case. Consider the combination UG. So suppose UG does not appear that often. But however, whenever U appears, it is followed by G. And whenever G appears, it comes after the letter U. So if this is the case, that U and G never appears separately, it definitely makes sense to combine U and G together to become a new element, or in our terminology, a new token in a dictionary. And maybe we should discard U and G. The assumption that every U is followed by G and every G follows a U. So if after UG is added into our dictionary, there will be no words is needed to use U or G, at least in our training data. So it is arguable that we don't even need U and G, we only need UG. But in practice, we probably still want to keep them because maybe we are going to read some new text, and in the new testing text, that UG are separated. U or G are used separated. But anyway, in this case, it makes perfect sense that we put UG into our dictionary as a new token, even though UG does not appear that frequent. So let's consider the situation on the opposite direction, that UG appears very, very often. Then, because U appears a lot and G appears a lot, so even though maybe U and G has no meaningful connection, but just because they appears very, very often, so there are some chance, so there are some good chance they are next to each other just by chance. But UG itself doesn't have much meaning itself. So by considering these two cases, we probably should sort of normalize the frequency, normalize the probability of UG by the probability of U and the probability of G. So that is exactly what PIS does. So instead of considering the frequency of UG, it divides the frequency of UG by the frequency of U and the frequency of G to get a relative probability of UG. And if the relative probability or relative frequency, and by consider this relative frequency, we find the most frequent combination, the most frequent pair, and put it into the dictionary. So that's the difference between WordPiece and BPE. Another popular method is called the unigram. Recall that we have introduced the n-gram. Unigram is the special case of n-gram, that is the 1 gram. So we can use it as a language model. So unigram is just 1 gram. So by considering it as a language model, we can compute the likelihood. The algorithm of unigram for tokenization works the opposite direction. The unigram tokenization starts with a very huge dictionary. Then it progressively trims down the symbol that is less useful according to the likelihood and the language model. So get a smaller and smaller dictionary. In practice, it often used with the sentence piece algorithm. So what the sentence piece does? It solves one important issue in the original BPE and WordPiece. That is, it considers the space as a character. Instead of doing the counting and the statistics on the words, the sentence piece directly works on the raw text without requiring some pre-segmentation. So you can use a BPE or using a unigram to design the vocabulary, to construct the dictionary, but it doesn't require any pre-segmentation. So it is particularly useful for language without clear word boundaries, like Chinese, Japanese. So let's move on the pre-train of language models. 10 years ago, the most popular way might be just simply use the word-to-vector to do. The most popular way is to train a word embedding models like a word-to-vector, and then use these models to compute the embedding of each word. So we start from a sequence of word into a sequence of embedding. This sequence of embeddings using a model that deals with sequence, like sequence to sequence or LSTM. The downside of this approach is we still have a lot of parameters that need to be trained from scratch. So the current mainstream method is to train a big pre-trained model that is trained on a huge text dataset, and then fine-tune it for downstream tasks. The pre-train is done by using some self-supervised manner. The self-supervised text is mostly some sort of sentence reconstruction, kind of like what we did using the auto-regression. The auto-regression, or more specifically, auto-completion, can be considered one of these type of the task. So as we talked before, it's just a kind of glorified auto-completion. The thing is, models can learn a lot of different concepts or things from this kind of task. So for example, consider this sentence. She put on her high heels, and this one is a crossword that we need to fill in. The brand is likely to be filled with something like went out or attend the party, but not went jogging. So although all these options are grammatically correct, but because she's putting on her high heels, So we know that she is unlikely to go jogging, which means if the model want to fill in the blank correctly, the model really want it because the model is trained by minimizing the loss. So if the model can guess this word correctly, it will get smaller loss. So again, if the model want to guess this blank correctly, and the model actually won't, it is best the model can understand the context from this condition, from this sentence. Otherwise, it is very difficult to choose the right word to fill in. So potentially, or at least in principle, the model can learn something of the model can have some contextual understanding from this type of training. Now consider this example. If it runs very well, so in this blank we should fill in some appropriate verb. So by this kind of task, the model can learn the rules of language syntax. Okay, then let's see this sentence. The cat chased the mouse right before it something. So first of all, the model have to identify this it is the mouse and see in what is actually happening. The event that the cat chased the mouse is before what it does something, which mostly implies that after it did something, the cat stopped chasing the mouse. So we know that this word might be escaped or hit. It's likely to be escape or hit. So the easiest way to fill the blank correctly might be to in fact understand what this sentence means. I'm not saying the model really understands it, because there are a lot of debate on what exactly means by understanding. But at least in principle, the training data already provide some information that understand it is a apparent way to solve the task, or at least arguably the easiest way to solve the task. Okay, this kind of task also provides some possible source of common sense knowledge. For example, like this one, I went to the ocean to see the fish, turtles, seals, and something. So this something is likely to share some common properties between all these three ocean animals. So it might be whales or dolphins. So from this kind of task, the model is potentially to learn some common knowledges. And in this sentence, he forgot to set his alarm, so this mostly likely to be was late or missed a bus, or so this is likely to. So this blank might be was late or missed his bus. So are given a chance for a model to recognize the cause and effect within this context. And in this type of sentence, the model might be able to learn the temporal sequence. There are more examples like, say, today is Wednesday. What day is tomorrow? Or for locations, like I'm living in Taiwan for 10 years. Mostly I stay in blank city. So this type of questions helps the model to learn the relations between geographic entities. So also you can learn some cultural relevance from this type of sentence. Like during Thanksgiving, we usually eat. So of course it might be turkey. Of course it is turkey. So not only we know that turkey is correlated with Thanksgiving, we know that it's something that we eat in Thanksgiving. And also, this is not a complete list because we have a lot of different data because we have a lot of text data. There are a lot of different information contained in text data. So by doing a simple text like just a crossword blank filling, the model can potentially learn a lot of different knowledges. At least we cannot rule out these possibilities by simply saying, okay, this is just an auto-completion. It is just an auto-completion. By becoming a perfect auto-completer, you have to know a lot of things. Okay, so let's go to how we actually train the transformers or the encoder-decoder architectures in general. We can train the encoder only, or we can train the encoder-decoder together, or we can train the decoders, or we can train the decoders only. So to train the encoder, one way to do that is we mask some words out of the text and ask the model to predict or in this context, to inference, or in this context is more suitable to say to inference the word that is being masked. One of the most famous example of this type of training is BERT. To be specific, the BERT has 3 different kinds of inference tasks. One is that we have mentioned before, that is to inference the masked word. And another situation is we replace one word by a random word. And the third one is we keep a word unchanged. But since the model doesn't know this word is changed or not, so it is not a trivial test. It still has to figure out this word is proper in this sentence. The model needs to figure out which one is the replaced one and which one is not replaced. In the training data set of the BERT, 15% of words, in fact, they are tokens, but by giving the example, it would be easier to use the word. So when I say word, in the reality, they are referred to the token that is split by the tokenizers of BERT. Okay, so 15% of the words are randomly selected so that the transformer are going to inference what is the correct words. 80% of these words are replaced by a mask. 10% of it are replaced by a random word. And another 10% are unchanged. So this type of training makes the BERT becomes a very popular pre-trained model, maybe like 5 years ago, or BERT becomes a very popular pre-trained model for a while. It can be used in a lot of different downstream tasks. However, since our course is generative models, in the realm of generative tasks, this type of encoding is not particularly, the pre-trained encoder is not particularly suitable for this type of task. So one way, it can still do the generation. So one way to do that is, okay, maybe we can just give some initial words and mask the rest of them. And then we ask the pre-trained encoder to predict the words. And if we wish the sentence to be grammatically corrected, we might have to want it to predict the word one by one. So it is not very nature and not very efficient. And for quality wise, as far as I know, the current mainstream method is still using the decoder base, because the decoder can do it more naturally by using an autoregressive way to do the training. To train a encoder-decoder pair, there are many ways to do that, but one popular way is to do it by masking some of the word and give this word some special token. So one way to do that is to mask out some part of the sentence and give each part a special unique placeholders, and then ask the model to decode the spans that were removed, and ask the model to decode out the spans that were removed. To pre-train a decoder, we'll treat it like a language model and simply in an autoregressive way. So when we say a language model, we mean we train it using this formula in an autoregressive way by given the first t-1 tokens, and we are going to ask the model to predict the next one. So the pre-training decoders is more naturally suited for the task of text generation. So start from GPT-2, this kind of model. Start from the GPT-2, a decoder-based model generate surprisingly good quality of text, and the model get bigger and bigger. People observe that a phenomenon called the in-context learning, which is a way to make the model to do some kind of learning without using any gradient. This happens when we observe that this phenomena appears when the models becomes large enough. So what is in-context learning? A typical example in GPT-3 is that if we're given some example of the English and the French pair of words, like thanks and mercy, hello and bonjour. If we give a few examples and give one that contains only English, then the GPT knows how to complete the sentence. Then the GPT realizes this one is going to do the translation. So it will translate this English word into French. Because we are in an era that chat AI is very popular. So one variation of this type of in-context learning is we give instruction as a prompt and maybe given some example so that we can ask the model to do something that may not be designed, or we can ask the model to have certain behavior or to finish certain task that is not exactly in the training data. So one famous example or tricks is the chain of thought prompting. So the standard prompting looks like this one. We give a question, math word questions. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So if we do a computation, if we do a calculation, we can find out the answer is 11. So the prompt, so we give a example answer here of this question, and we give another question here, and hoping the GPT can complete the answer. It turns out, at least for the GPT-3 that the paper used, it doesn't output the correct answer unless it changed the prompting a little bit. So here, the key difference is that the example answer does not simply give the answer itself. It also gives the description of the reasoning process. So the major find out of this paper is finding that by given this example, it will significantly increase the chance that the GPT answer correctly. It applies this type of strategy of this type of prompting tricks in many different texts. Most of these texts require some sort of reasoning, complex symbolic reasoning. And it turns out it works very effectively. There are many different tricks there are many different methods that we can use in the prompt to improve the quality of result generated by GPT. But this one is probably one of the most popular. So now let's discuss how to actually generate the text at inverse time. So recall that our language model output the prediction probability of the next word or next token. So we're using softmax to generate the probability. First, we output a logic for each word. Then we feed the logic into exponential. So it becomes a positive number. Then we normalize the number over the summation of all exponential. So we get a probability. So recall that in our homework, the way that we generate the text is using this probability. So we're generating the word. Actually, we generate the characters according to the modeled probability of next word. But another way to generate the text is using a gradient decoding. That is, you didn't randomize the generation. You simply generate the most possible word for the next word, and after you get the next word, and you generate the most possible next one. So there are some scenarios this method makes more sense. For example, if you wish to generate a translation, if you are doing machine translation, you probably don't want to generate a sentence that is correct in 90% of time, but incorrect in the rest of 10%. You probably want it to have a consistent output. So generate something, achieve the max probability or maximize the likelihood makes sense. However, if you're doing so, it is likely you're going to generate repeated words. You're going to eventually generate repeated words. So this one is a typical example. Even if you generate the words randomly, you probably still occurs this situation, this repeated word situation. And even if you are using some advanced model like Google's BARD, or maybe sometimes ChatGPT, there is some chance that you are going to generate some repeated words. But this situation is especially bad if you are using greedy decoding. So how do we avoid it? So why does this situation happen? One reason is that suppose you already generate two, say I don't know twice. You probably then this makes a pattern. So it makes more sense to generate the third I don't know, because we are generating in an auto-regressive way. So for all the model know, these two I don't know is the given words. So if you already have two I don't know, it is likely we should generate the next one. And you definitely should generate I don't know if there is already like 10 or 15. So the y-axis is the negative log likelihood. You can see that after a few iterations of the generation, you can see that the model gets more and more confident after it generates a few, I don't know. After it generates a few repeat words. So if you are generating a lot of text, chances are some of the text at some point it is going to generate some repeated words. And if it is a case, it will increase the chance it repeat it again. So once you repeat, you'll never go back. Kind of like the next graph here. Once you repeat, it's going all the way to the infinity. So the obvious solution is to generate it randomly. So at least it got some chance to break the loop. So at least it got some chance to break the loop. However, just like what we did in our previous homework. However, this doesn't mean this method is perfect. It's got its own issues. So one issue is the long tail issue. Because we are generate the probability using softmax, so we never get a word that has exactly, we seldom get a word that has a probability exact 0. It can be very, very small, but usually non-zero. The reason is that if we wish to get a 0 from, if we wish to get the 0 from softmax, the logic has to be negative infinity, because exponential negative infinity is 0. So you can see that although the probability will concentrate on a few words, but a lot of words are getting some small but not 0 probability. So although each of the words has a very small probability, but we have a lot of different words. So the summation of all these tail words may get a chance to be output. We may have a chance to pick those words that has a very small probability. But in fact, if we have an ideal model, this probability should be 0. One way to do that is top k sampling. So we fix a number k that we only choose the most possible k words and discard the rest of them. And it is pretty naive. But it works in many situations. It works in many situations, but you can imagine it can go wrong. So one typical example. So here is an illustration of the possible situations that top k sampling doesn't work too well. So one example is that we cut the word too early. We cut the list too early. So there are a lot of words we might wish to keep, but so there may be more than k words that we want to keep. On the opposite, another situation is that we cut it too late. So that means the real choices is less than k. So if we cut the first k words, so if we include the 10 most likely words, we're going to include some words that we don't like it. So none of this situation is too serious, to be honest. So if we cut too early, we still got healthy options that we still got a healthy options. We still got a healthy alternative that we can choose from. If we cut it too late, although we included some unwanted word, but since all of them have a small possibility, and we don't have a very long tail, so they are very unlikely to be chosen from. They are very unlikely to be chosen. But still, in principle, top K doesn't seem to be ideal. And these two situations are not just some theoretical imagination. They actually happen quite often. So another way to do that is top P sampling. So we have so we don't cut the list in a fixed number. We keep the words until we reach accumulate probability to a certain threshold, like 90% or 95%. So because so this method seems to be more smart. So suppose we have only one candidate with very high probability, we are likely to cut the list to be shorter. If we have a lot of equally possible choices, we are going to have a longer list. So both top K and top P are very common options that you can adjust when you use pre-trained, when you use an off-the-shelf language model. But the idea of them are pretty straightforward. So I hope after this explanation, you have both of them are not perfect, but I hope that after this explanation, you're going to understand how they work. You're going to understand how they work and adjust your value of top K and top P wisely and more confidently. So another common parameter that you can adjust when do the text generation is temperature. The idea of temperature is to scale the probability. We are still keeping the order of the probability, so that if a word is more probable than another, so after we scale it, so we don't change the order of the possibility of different words. However, we can adjust the temperature so that we can change the temperature to manipulate the probability. So either the words with high probability become more possible to be chosen, or we are making the words to be more equally, or we are going to make the distribution to be more uniform, so that words with less probability is going to increase the chance of the words of low probability to be chosen. So there is a parameter tau here. We defined each logit by this tau. So if a tau is going to be a very large, S divided by tau is going to be close to 0, so that exponential is going to be 1, which means when this tau is very large, PT is more likely to be uniform. On the other hand, if tau is going to be smaller than 1 or very close to 0, then the large logit is going to grow more quickly than the logit that is smaller, because we have an exponential here. When tau is very close to 0, then only the top one most possible word is going to be chosen. In other words, when we raise the temperature, we are increasing the diversity of the output. And if we are lower the temperature, we are going to increase the certainty of the output to be more greedy sampling like. So the property is going to concentrate on top words. All of the above adjustments are doing in the inference time. But there is an obvious, maybe we can say the issue or potential issues that occurs in the training time. That is, we are actually feeding different input to our model in training time and in inference time. In the training time, we are feeding it the ground truth sequence as an input when we do the text generation. And when in the testing time and when in the inference time, we don't have a ground truth, so we are feeding the output as a next input and so on. If we have a perfect distribution model, then this won't be much issue. However, we don't have a perfect distribution. There are even slightly difference between the real distribution and our model. This iterating process will emphasize the differences. This bias is called the exposure bias, and of course, this is not something we choose to have. The reason that we use this different way in training and in inference is because we cannot feed the output as the next input when we train a model like what we do in the inference. Because if we do so, we don't know how to calculate the loss function because if this one is not in the training data set, we don't have the correct output. We don't know what the correct output is. So on the other hand, obviously on the inference time, we cannot do the same as the training because we don't have the ground truth. So although these differences in the training and the inference or the exposure bias is not ideal, there is no simple or obvious way to solve the issue. So one way to do that is we can feed the output to the next input, but we don't have to do that for every single input. We just give a small probability. We only do that for a small probability. So after the model is trained, we can increase the probability a little bit we can increase the probability over the course of training. This method seems to be reasonable, but it is not entirely clear that how we should define our loss function. So it seems to be work at least in some tasks, but currently I don't think this one is used in mainstream. The most mainstream method right now is using the reinforced learning from human feedback. So another issue is, before we're going to talk about reinforced learning, before we're going to talk about RLHF, let's talk about what does it mean that the model does not align with user intent. So this one is a typical example that for GPT. So suppose we give a prompt, explain the moon landing to a 6-year-old in a few sentences, and we ask GPT-3 to generate the text. Instead of answering the question like what human being might do, like a human might do, it is very possible that GPT treat this one as an example, like what we talk about in context learning, and give more example like this one, like explain the theory of gravity to a 6-year-old, explain the theory of relative to a 6-year-old in a few sentences like this one. So that is because we are training the model to complete the sentence in a more general setting. And this setting may not align with what we intend. This may not align with our intention for what we wish the model to output. So a simple solution is we collect of instruction text. So there are some instruction on how we directly encode our intention as a text and tell the model to follow the instruction to do the output. So after this kind of fine-tuning, it seems that the model can generalize. So when it sees some text that it has never seen before, it can still follow the instruction and do what we want to do, what we intend it to do. Because this method is very useful, so there are very active research on this approach. So although we call it instruction fine-tuning, the dataset is really huge. So for one example, the Supernatural instruction dataset contains over 1.6 thousand texts and over 3 million examples. So this method is still a solid method that people use today. So the first famous model for this method, for using this method, is the Flan T5 model from Google. So here is an example. Before the instruction fine-tuning, so when asked a single choice question, it doesn't actually do what we intend it to do. But after the instruction fine-tuning, it definitely will reply something we are expecting it to reply, and correctly. Although instruction fine-tuning is very useful and straightforward, but it doesn't address the issue of exposure bias. It doesn't address the exposure bias issue. It doesn't address exposure bias. So is there a way that we can, so if you have a way to give feedback in training, when the model generates something outside the training data set, it would probably solve our issue. So suppose we have human feedbacks, because obviously humans can give our feedbacks no matter the generated text is in the dataset or not. So we call that the human reward. This is terminology from reinforcement learning. This is a terminology. Reward is a terminology from reinforcement learning. So if we can obtain the human reward, is it possible to solve our issue of the exposure bias? One of the famous achievements of reinforcement learning is AlphaGo. So the best setting of the reinforcement learning is that we have an agent in an environment. The agent has some choice of action. The algorithm of choosing which action according to the environment is called the policy. So what the model we are training is the policy of the agent. So after a sequence of actions, the environment would give the agent a reward. The real reward may be negative if the agent did something really wrong. So the difference between the reward and the loss function is that, first of all, you can do the gradient descent and the backpropagation from the loss function to the weight, but the reward does not. We don't know the formula between the policy. The agent doesn't know how to compute the reward from the policy because the reward is given by the environment. So it cannot be using gradient descent directly. The other difference is that the reward is only given after a sequence of actions. So maybe some of the action is correct, maybe some of the action is good and some of the action is bad, but we only get a accumulate result of the sequence of action. So we don't know which one action in a sequence is good and which one action in the sequence is bad. We only know that this sequence seems to be better than perhaps the other one. There are a lot of different studies on reinforcement learning, and one of the methods is called the policy gradient. One type of the method is called the policy gradient. So this is a major tool to do the optimization on the assumption that we can get some rewards, on the assumption that we can get some human rewards. So the apparent issue is that it's not easy to get human rewards. Either it is very expensive or we just don't have enough human to respond to the text generated by the model. You can imagine that we need a lot of human because in the training we are going to have thousands of steps. So if we need human to give a reward to every sentence that the model generated in the training, it's going to be very, very expensive and maybe very slow. So one way to get around this is we train a model that learns how to give rewards like a human. So you can imagine that we already collect a lot of data that human gives rewards, and we train the model in a supervised way to give the rewards from the given text. Although it doesn't seem much because we still need to train a model, or instead one model to train, we have to train two models. One is a generative model and the other is the reward model. But the thing is, reward model is a supervised model and it's much easier to train than the generative model. So this is still a step forward. And in fact, we can actually evaluate how good this reward model is. So after collecting a lot of data to train this reward model, and the performance of this reward model is acceptable, which means it kind of close to what a human does. The performance of a reward model is close to a single human. The human ensemble is still better, but at least this reward model is close to a single human. The other problem is human judgment are very noisy. So one person may think this one is very good and give the score like a 7 out of 10. And another guy may think this one is not good and also give a score 7 out of 10. So there are inconsistency between different individuals. Even with the same individuals, time to time, the standard of giving score may vary. So one way to make this score and the rating more reliable is instead of giving an absolute score, instead of giving this score in an absolute scale, we're asking people to give a pairwise comparison score. So for example, we are given a question and we collect 3 different outputs. Then we can ask which one is better and which one is worse. So this score is more reliable and easy to train a model, because this one is simply a classification. Or maybe just this one is as simple as a binary classification. Instead of a regression, this one is a binary classification. So it turns out this RHF reinforced learning from human feedback is very good. So by combining this reward model with a policy gradient method, with a policy gradient reinforced learning algorithm, to specify the PPO, proximal policy optimization method, the result is pretty significant, better than using instruction fine-tune alone. So the GPT is using this RLHF at scale and get a very fantastic result. So here is the result. With the same question, the GPT, which is fine-tuned from GPT-3, can give an answer that we are expecting. And the same here, here's another question. And here is another prompt. Write a short poem about a wise frog. So instead of making some more examples like this question, the GPT follows the instruction, follows the prompt, and actually write a poem about a wise frog. ChatGPT is using the same way to train, but on a dialogue data instead of the instruction data. ChatGPT is using the same method to do a fine-tuning, but specialized in dialogue data. So to summarize, the method is first training a generative model using the instruction fine-tuning, and then we can generate comparison data and ask human to evaluate this comparison data. Then we train a reward model from human feedback, and then using this reward model with PPO, proximal policy optimization, which is a policy gradient reinforcement learning algorithm, to train the final generative model. Okay, so we are covering the major concept and method for training GPT, ChatGPT, or InstructGPT. So next week, we are going to study the implementation of GPT in detail.